Hi. Hey, Rahul. How are you doing? How are you?
Doing great. How is, you said Portugal, right?
Yeah, I'm in Lisbon. Not forever, but for the next year or so. Yeah, I'm working out here.
Is it a client that's out there, or you just want to be in that kind of like environment?
It made sense for me visa wise and like career wise and for to start my career here. Well then like just because of what we're doing at Cloudflare at the moment. And we're growing the office here very fast.
Okay, so right, so it's a work office right there. That's great.
Yeah,
That's
yeah,
awesome.
we do have an office. Oh, yeah. I didn't understand what you were asking. Yeah, we do have an office, and like Cloudflare is heavily investing in it, so it felt like to start off my career in a place where we're going to be hiring a lot of people for our team in particular.
Sure. Yeah. No. I mean, what's interesting is tech grows globally in different regions at different times. So I had one friend of mine. He made his career by moving to like Southeast Asia or something like that.
Right.
But this was like 20 years ago, right? And so, but like different places have hotspots. Is someone else in the room? Okay, yeah, there's someone.
Hi, Manisha and Dinesh.
Okay.
Hello, everyone.
Hi.
We're doing the Rahul thing where we're sending a
The
message.
ad here. You got to be bold, man. Got to be bold.
I missed the last session.
No worries. Hi, Raj. Yeah, let's wait for a couple more minutes. I think the conversation here is going to be reasonably short. The paper is actually very straightforward, but it's fundamental. It's super famous. It's so famous that it's like the default material in the class now. And everyone goes over this at some point. So it's good to read the original source, but it's not very long. Yes, I think we can chat for a couple of minutes. How are people? We still don't have those review topics, do we? No.
Did professor posted the topics related to the paper?
Yeah, let me post. Oh, I think she hasn't. But let me post the paper.
It's for sure just going to be literature reviews, right? We're not going to be allowed to do project like coding projects, like working things.
I think it's just a review.
Okay.
Who is taking CS 410 in here?
I am.
Okay, there's a bunch of us. There are going to be projects in that class. So.
Yeah, that's what I was thinking is like do a literature review for this class and use it in that class. Right. Use the results of that from the other class. So that way you have some insight into what your project is.
Okay. Right. I just learned. Okay. Let's see. Is this gonna work? So I use this notability thing, and I don't know about you people, but like when I read stuff on my screen, I have to point to myself what I'm reading. Like I'm constantly pointing at the things where I'm at. But this highlighter for some reason is only available when you're sharing screen. Like once I stop sharing, I can't use the laser pointer. And that's my favorite feature of Leah. That is, I don't know why it's not there permanently. It's really annoying. Okay. Boom. What are we talking about today? I'm talking today about the sequence-to-sequence learning with neural networks paper. So it's a paper, but by 3 superstars in the machine learning world. You probably have heard of Ilya, we share the name, and Kwok. I don't know the middle name, but Lei. Raj actually linked his speech talk last week. It's in the channel if you want to see it. About what is it about, Raj specifically? He talks about a bunch of stuff there. It actually includes the stuff we're going to be talking about here, but I think it's also about the tension model. I'm not sure. I didn't watch all of it. Anyhow, and Oriel, I'm not sure about him, but I'm sure he's also an important person. Anyway, the point of this paper is kind of we have seen in the class, we have seen a lot of different language models. We have seen n-grams, we have seen neural n-grams, we have seen generative models where we know we can generate text, right? And we know we can classify text. We already know a bunch of methods with both statistical and neural methods. But the problem with all of those is that they accept an input, which is a vector, and they most of the times produce an output, which is a vector, right? And it's not obvious, and we actually and it's not obvious how to process non-vector inputs, such as when you have a sequence of vectors. Like, right, if I want to build a tool such as Google has, where I get an email and I want to make suggestions for email responses, right, I need to process the entire email as a sequence and then output a different sequence, a sequence of a probably different length than the input. And like, how do I represent this with a vector? I probably can't do that. With n-grams, we talked about different methods where you can concatenate them. We know how to do vector embeddings. We actually, I think some of the readings mentioned in the class talk about how you can take a couple vectors and if you don't want to concatenate them, you can add them up field by field. That's also something you can train a network on, but fundamentally, like, you're constrained to a fixed number of units in your input. So it's an open question. How are we going to process sequences that output different sequences, right? And what had been invented before this paper was published is recurrent neural networks. And we're going to talk about how those work. And this paper specifically mentions LSTM networks a lot, which are just an advanced version, a slightly more complicated version of an RNN. And we're going to talk about how those differ. So this paper took the pre-existing methods of using LSTMs, which are recurrent neural networks, and applied them to the machine translation task, where you have an input sentence and you produce an output sentence with probably of a different length than the input sentence and in different language, right? That's a fascinating task, and they didn't apply many statistical methods here, not much optimization, but as we will see, it worked very well, right? So, so how does this work? Right, so despite their flexibility and power, DNNs can only be applied to problems whose inputs and targets can be sensibly encoded with vectors of fixed dimensionality. And this doesn't address our problem of processing sequences. So, okay, let's actually look at this diagram over here. So this is a very high level overview of what a recurrent neural network looks like. Can I? Okay, I'm going to keep this at the top of my screen. And the other thing we're going to be paying attention is this formula over here. So what a recurrent neural network does is that it has a bunch of units, right? These guys over here. Each of these units gets a word from an input. Let's talk through this in the context of processing a sentence that we want to translate. Every word in the sentence, right, is a vector. We produced embeddings for those. So every unit here takes one word as an input and produces what is called a hidden state. So I should phrase it this way. Every cell over here takes a word as an input plus a hidden state output by the previous cell. And you could have over here a sort of an initialization hidden state, and you see that all these objects are of the same structure, but they are sort of recurrent, right? One of them gets the initial input and the first word, and the second one takes the second word and the output of the first one. The third takes the third word and the output of the second thing, the output hidden state of the second unit, and so on and so forth. And it so happens that the third unit over here has the hidden state that encapsulates the knowledge both from the second unit and the first unit. So how does this work mathematically? So this hidden state, HT over here, is the recursive part. We have our unit xt, we have a sequence of inputs, right? Each x over here is a vector. We apply a transformation to the vector, and we apply a transformation to the hidden state that we got from the previous cell. We sum them up, we apply some nonlinear function to them, and we get our hidden state that then will become the input to the next, for the next cell over here, right? And we can do that indefinitely. We only need to train these matrices once, and then they can be reused for every cell. And it doesn't matter. We don't need to know ahead of time what the length of our input is going to be, right? And then if you want to produce some output, right, your cell over here, so you have your hidden state, you can apply a different transformation to it and possibly produce the output, some output over here. Cool. So any questions so far? What do people think?
Just one quick question. The weights for the hidden state, the recurrent weights, are they separate?
No, they're not. So that's the thing. You train one set of weights, this one matrix for your hidden states, and it's shared, right? You don't know ahead of time how many of these units you're going to have. You just train conceptually. You just train one instance of these, and you just replicate it based on your input. If you have an input of 20 words, you use 20 instances of these. If you have an input of 2 words, you just apply it twice. Does that make sense?
So well, I guess the question is, you're passing back something. What are you passing back? You're passing back the hidden weights, or you're passing back the output. Something has to be concatenated together in the hidden state, right? So I'm just trying to add up the math. Like, what is it?
So the hidden state is produced from the previous hidden state plus the current input.
The previous hidden state. So let's say the input is 1 character and the hidden state is 10, whatever, 10 values. So the current hidden state is 11. So then you're passing back the previous hidden state, which is 10. So your input is always going to be, let's say, 11.
You're referring to scalars here. I'm not sure I understand the question. So
yeah, I'm using scalars because I don't want to get complicated with the matrices.
Right.
Like, so if your input is 1 character, right? It's 1 character, and your hidden layer maybe has 10 nodes, right? So 10, let's say 10 values. So 1 times 10, right? And so then you're going to pass back those 10.
So let's work through a very small example. I guess I think that might be helpful. Okay, so let's say our input is our both input and hidden state are of dimension 2, right? Let's say that at step 1, this is going to be very hard to type. How do I? Okay, I'm just going to do text. Okay, step 1, or actually input. Okay, H0, the initialization, my initial hidden state is going to be 1, 1, just because I said so, right? It doesn't matter, or maybe it does, it depends on your training, but whatever. You need the initial hidden state to, we'll see how it works. And then my first input is going to be 1, 0, right? And then my hidden state 1 is going to consist of me taking the sigmoid of, let's say our matrix is actually an identity matrix. So W's here are identity matrices. So we don't do any transformations at all. So we just say then H1 is going to take X1 as the input plus the last hidden state, right? And well, this is going to be the sigmoid of 2, 1, right? You know what? Let's drop the sigmoid. Let's not have it because to make the examples simpler. And then if my word number 2 is, I don't know, 0.5, right? Then the hidden state that I'm going to pass forward is going to be x2. I take the second word. My next cell is tasked with processing the second word, but I also want to know the context of the past sequence that we have seen up to now. So, and the past sequence is encoded in H1, right? So I get, what do I get? I'm very bad with math, sorry, 2, 1.5. Okay, does this make sense? You're muted.
The hidden state is taking in the current X as well as whatever so it's a concatenation of the entire hidden state. And
concatenation, it's not concatenation, but where it's a transformation, I think that's a more accurate word.
so it's actually combining the two values, the two sets together prior to entering into the hidden state.
Right, we're producing the new hidden state, right? I have, like, what is the idea of the recurrence here? I have information about the previous sequence and I have my current input. I take my current input, I transform it, and I add it to the knowledge about the sequence, and I pass that knowledge forward. And then the next thing is like, okay, I got some knowledge about the past sequence and I got my new input. I take that input, transform it, pass it forward, and let's keep going. And we don't need to know ahead of time how many of those units we're going to have because we're reusing these matrices over here.
So it's a combination. It's not a concatenation, and that gives us the history because we've been. It's kind of like a transfer learning where we're incorporating it in.
Right. So here is a nice illustration. This is from Andres Karpathy's, I'm probably butchering his name, blog. The unreasonable effectiveness of recurrent neural networks. I'm going to link it later. You can use them in very different ways, right? This, I think, many-to-many is the most obvious one, right? So red ones over here are inputs, blue ones are outputs, and the green ones are hidden states. So each green cell depends on its current input plus the previous hidden state. And each green cell can also produce output if we want to directly start outputting something right away. A different example would be this I'm not pointing. This many-to-many, right, where we first encode the entire sentence, and then only then, after we encoded the entire sentence, we start producing output. You could do different things. If you want to do a classifier, right? If I want to, you can build a classifier with a recurrent neural network. If I want to take the entire email as an input, I want to build a vector that encodes the information about the entire sequence, all the words in the email. And then I want to do a normal feed-forward neural networks based on that to do some classification like spam, not spam. Spam, I can do this architecture, right? I process all the words first in a recurrent fashion. Then the output of this guy has information about the entire sequence, and then I can just do any of the classifier methods that we have done before in class. Does that make sense? Okay, so there's going to be more examples. I think this sort of looking at this from different perspectives will help you internalize as we keep going forward. So the interesting thing about this over here is that the simplest sort of, if you had to come up with an RNN on your own, what you could do is say, okay, how about I just make my hidden state at each point, just the sum, non-transformed sum of the past hidden state plus the current vector. I'm just going to be summon them up all the time. Why don't I do that? That sounds like a great idea, very simple. The problem with that is that it's going to be a linear function, right? You keep summing up. It doesn't depend on what order you sum this up. And that means you are not encoding the sequence, right? I can swap the two words. I get the same result as the hidden state. That's why we want non-linearity in our hidden states, right? I think that's a very interesting point here. I found this in an obscure textbook. People don't regularly even hypothesize about non-having hidden non-linearity here. Anyhow, so this is a description of what's called an element network, which is the simplest, the oldest instantiation of an RNN. It's very easy to understand. It has its problems, though. One of the problems here is the vanishing gradient problem. If you think about it, what you're doing is you're taking the previous hidden state at every point, and then you're adding something to every single value of that hidden state from your current input. And that means that you're sort of more heavily prioritizing more recent input than the latter I guess, input from longer ago, right? That's a bit of a problem. You still have your hidden state, that's good, but there's a bit of an imbalance. So what these LSTMs do, long short-term memory networks, those are recurrent neural networks, but the idea there is do something like, how about at each step, when we produce the hidden state, we do what's called gating, right? So my hidden state is let's say it's a 300-dimensional vector. And then at every cell, recurrent cell, depending on the input, I'm gonna say, okay, 150 entries of this 300-dimensional vector are not important anymore. I'm gonna override them with my current input. But the other 300 or 150 entries in the vector are important, I'm gonna keep them. So essentially an LSTM lets you train an additional thing that's called a gate, which right, and it's dependent on the index of your cell, and it's going to depend on your input, but it's going to produce of a vector of 0 and 1s, okay, etc. And then you will be able to, the idea here is that you're able to preserve information and then only affect information that's not important anymore, and you can train the neural network for it. You don't need to think about LSTM specifically, as long as you understand the idea of an RNN. General idea LSTM is the same thing, just slightly improved. The point there is that LSTMs are slightly better at processing longer sentences. The problem with raw RNNs is that they kind of over time they forget about the stuff that happened a long time ago. LSTMs are still able to figure those things, long-term dependencies out.
So just a quick question. So recurrent neural networks, the downside is it's kind of like an exponential moving average, right? It's overweighting the recent stuff. Mm-hmm. And then LSTM is an improvement because half of the hidden values are being masked in some way.
Right. Yeah. Not necessarily half. It depends on how your network works. But yeah, some of them, your network is able to figure out like, oh, this looks like an important context from this word. I'm going to use it, but the rest doesn't look important, and I rather not override what I had before, and I should preserve this. But some of the old context is not needed.
I should preserve the hidden state, or I should preserve just input as it is?
Both, right? You have your hidden state and you want to produce some new hidden state. The question is how much of the current hidden state you're going to overwrite heavily with the new input, and how much of the hidden state you're going to try to preserve.
Okay, so it's just maybe it could be even like on every single node in the hidden layer, it could be like a different percentage that it's keeping or letting go.
Right. Yeah. Exactly. So that's the idea. So okay, someone sent a message back in 5. Okay, right. Okay. Anyhow, so boom, 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 boom. What can we do with these neural networks? What did these people do? The simplest strategy for general sequence learning is to map the input sequence to a fixed size vector using one RNN, right? This is this case over here. You have a vector, you have your input, sorry, multiple vectors is sequence, and then the output of this guy, the last recurrent cell, is going to have the information about the entire sequence. And then to map the vector to the target sequence with another RNN, right? And this is exactly what we're doing here. We're going to talk about how to convert an RNN to a generative model, but in general, like, okay, so this thing produces a vector that encodes the entire sequence. Now we can use it to decode and produce a different sequence. And this is exactly what's portrayed over here, right? I have multiple inputs. I have end of sentence token. And as soon as I encounter an end of sentence token, I start producing outputs. I produce W, X, Y, and Z. And then once I hit end of sentence, I'm done. So the generative model over here is the same stuff as with n-grams, right? You keep producing until you hit an end of sentence token. But the interesting thing here is that you also have your hidden state as the input, and then you keep passing it forward. And
so that W input after the end of sentence was the previous output.
Yeah, so not only are you passing the hidden state, you're also passing what you just generated a second ago on the last step, right? So, and this is very interesting because the output cells over here are no different from the input processing cells over here, right? You could have an error here. You're just going to throw the result away because you don't care that early. So this is the exact same architecture, same thing here. Okay, so how does this work? I think it makes more sense once you look at the formula, so I hope that helps. The goal of the LSTM is to estimate the conditional probability of an output sequence. Sorry, I'm going to turn the lights on. Given the input sequence, right? X's here are an input sequence and Y's are output sequence. An important thing is that T prime here may differ from T. That's the innovative part. The LSTM computes this conditional probability by first obtaining the fixed dimensional representation V of the input sequence, right, given by the last hidden state of the LSTM, and then computing the probability of the entire output sequence. Okay, so this is what we want to compute: the probability of generating an output sequence given an input sequence. And how do we compute it? Well, we just multiply probabilities of producing every single output word in the output sequence conditioned on the hidden state encoding the input sequence plus the preceding output words. So V over here as this guy, right? Well, it's sort of a combination. Again, so every output node is conditioned on the hidden state and the thing that was just produced. So it knows about what had been produced before. And then if you want to generate a sentence, you can generate it by either picking the most probable YT at every step until you hit end of sentence, or you can do a clever algorithm like we talked about beam search last time to produce the most probable sequence globally. Okay, do we have any questions so far? I've been saying a lot of words. I'm hoping people are not too confused, but if you are, let's get them unconfused.
I have a slightly different question. When was this created?
This is 2013, I think.
2013. Okay.
Yeah. So Ilya, Rahul, do you have a question?
Yeah. What's up? 2014. Yeah.
Okay. So I don't have as such question, but I just wanted to discuss like we're generating words on the second half, right? And you just mentioned that it is the same architecture. And earlier we were generating some sort of error, maybe, I don't know. So in the second half, like, how do we know that it's the correct word and it's not the error? Like, is there any differentiating factor? Like, I mean, we can assume that from the second cell itself, there is some sort of generation of sentence, and otherwise, like, there's no difference. Like, how are we differentiating?
Sorry,
You know, you use.
can you say the question once again?
Yeah, so I was saying that on the second half of this architecture, you can see that there is word generation. And so is there any reason why we are, this second half, I mean, we start generating W, X, Y, Z. So, I mean, is there any reason mentioned in the paper, like why we consider it as a word? And is there any way to improve it if it's not the, expected, or maybe it's not making sense? And how, like in the initial ABC cells, like they were generating errors. So like, how is it different from this W? Like, is it possible that?
I think that's actually a fantastic question. I wonder if you already know the answer, because I think that's a very, so if you forget about this part, just cross this out, right? You could build a generative model that just tries to predict the next word, right? You could try to build a model where when the input is A, you should output B. Once you see B, you should output C, right? And then, well, I guess here you get EOS, right? Okay, this is almost, this is so hard to write. You could build a model like this, and it is actually a very famous trick to train such models by what's called teacher forcing. So what you do is that you let your model, given A, produce some output, and let's say it produced, I don't know, N, the letter N, which is not correct. It should have produced B. Then teacher forcing is a thing where you keep training your model as if the model produced B over here. So you still keep B as an input to the second cell. And you still keep and you use the hidden state that was produced even though the model outputted N, right? But you force it to take B as an input so that it's more resilient to incorrect hidden state with failures in the past. Does that make sense? So teacher forcing is this idea that even if a cell at some point, at some iteration, failed to produce the correct output, you still train the future cells as if the previous cell worked correctly. So answering your question over here, I think, well, again, here, even we could train the model, even if it produced not a W over here, but something wrong during our translation training process, you could still input W over here to make this thing keep thinking as if everything worked well, right? Does that make sense? I think that's what you're asking, or no?
I have one question here related to the Denise questions. So,
Yeah.
like, if first unit will give output B, you said M, right? Then how the second unit will take input B? It will take that M, right, as an input.
So, well, it's up to us, right? We're ultimately, we control the code, so we could ignore this and still feed in, during training at least, the correct input. Does that make sense?
Mm-hmm.
Okay, cool. Boom, 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 boom. So
I was on mute. Sorry for that. And yeah, I was just saying one thing, that you mentioned that we can have W as the output. So this is not the training part, right? That second architecture is the outcome. So I really don't expect that we will be sending our own outputs. So the other thing is that I wanted to think was, is there any mention in the exam? Oh, sorry, why do I say it exam? In the paper, like, is there any way to improve the output generated by the second architecture? So if we are expecting some sense out of it, so is there any way to improve that?
Right, let's
second.
Okay, that's a very prescient question, because let's talk about the loss function. Okay, I mean, we'll get there in a moment, right? I just want to see. Okay, so one thing I want to mention, they mention this 5 times throughout the paper, and it seems very important to them. They train the model by reversing the input. I'm just going to read this out loud because I'm not going to explain this better than that. So our actual model differs from the above description in 3 important ways. First, we use 2 different LSTMs, one for the input sequence and another for the output sequence. Okay, so this means that you have 2 sets of these W matrices, right? You have three sets for the input processing network, and three weight matrices for the output. But let's find it, like, that's kind of intuitive, right? Over here is your cutoff. This thing has different coefficients than over here. Okay. Second, we found that deep LSTMs significantly outperformed shallow LSTMs. So we chose an LSTM with 4 layers. What is a deep LSTM? Well, no one prohibits you. If you have 1 green layer over here, you could just stack another green layer on top of it, right? And you could keep going, and they're like, you're a free person. You can keep doing this forever if you want. There is no theoretical. It's actually still an open question of why this works better sometimes, but it does. And they say that instead of using 1 layer, 4 layers work better for them. Whatever, they can do as they please. Third, we found it extreme. Okay, this is the most important one. They emphasize this so much. Third, we found it extremely valuable to reverse the order of the words of the input sequence. So, for example, instead of mapping the sentence ABC to sentence alpha, beta, gamma, the LSTM is asked to map CBA to alpha, beta, gamma, where alpha, beta, gamma is the translation of ABC. This way, A is in close proximity to alpha, right? B is close to beta, and so on. And that makes it easier for the stochastic gradient descent to establish communication between the input and the output. Again, it's just a heuristic. It worked for them, and they really emphasize this point. So again, this is interesting because LSTMs were used to address the problem of RNNs of forgetting things as time goes on. And these people are saying, actually, if we reverse the input, then our LSTM can do even better. And because it won't even have to deal with those long connections, the context will be, the communication will be much shorter, right? If my A over here is the last input and the first output, then my values are pretty close to each other. Okay. So decoding and rescoring, the most important thing, what's our loss function? The core of our experiments involved training large deep LSTM and many sentence pairs. That's great. We trained it back, maximizing the log probability of a correct translation T, given the source sentence S, right? So again, we're maximizing the log probability. Every log here is negative because P is from 0 to 1, right? So you're maximizing this value normalized by the size of the training set, right? So your goal is to produce as good of a translation as possible.
So here the loss is just based on the absolute magnitude or the size of the training, but the training itself is done in reverse order.
Mm-hmm.
Right, so there's no concept of that in the, right, that doesn't make any sense.
Right, yeah. Dinesh, does this help? Maybe you have a different concern. Maybe it is in there somebody.
Yeah, so I just wanted to know just one thing that, okay, I think it requires me to work it out. Maybe I'll post a question later on. We can proceed for now.
Okay, but again, we're trying to, so we have our training examples and we try to maximize the probability. Our model is generative, right? It assigns different outputs depending on the input, different probabilities. And we try to maximize the probability that it assigns to the correct training output, right? That's our training objective. And then once we train this model, then we given some input, the output translation that we get is the argmax, the maximization of this probability. Right. This
what are we translating this loss to? Like, what is the weights? What are the weights? Is the one that we saw in the hidden state formula? Those weights are getting affected by this loss function?
Yeah. So you're training 3 sets of weights. The weights used to transform the input, the weights that are used to transform the previous hidden state, and the weights that are used to transform the current hidden state to the output.
Got it.
And again, this is reused between different cells. You only train one set of these weight matrices per recurrent neural network. Okay. Boom, 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 boom. Where were we? I'm lost. Okay. We search for the most likely translation using simple left to right beam search decoder, which maintains a small number B of partial hypotheses, where a partial hypothesis is a prefix of some translation. Okay. So Raj talked about beam search last time when he talked about named entity recognition, retrieval, actually. And I didn't understand why beam search was important last time, and it didn't click for me up until today. So I just wanted to talk through this. I was like, why don't I just, so they're saying use beam search. And I was like, why don't you just produce your output model based on maximizing the probability by taking the most probable output word at every step? Well, the answer to that is that these probabilities are not independent, right? And ultimately, if I'm producing an output of length 2, I'm trying to find the 2 words that have the highest join probability. And these probabilities are not independent, and right, and they are given as such, right? This is one way of expressing this. And while we're actually, I'm going to do T2 given T1 times probability of T1. Well, that means to maximize this probability, I can't just pick the most probable T1, because that will affect this value over here. And I need to do sort of a look ahead and more clever strategy over here, because I want to optimize the global probability. I don't want to optimize just a single probability at every step, right? So my choice of T1 will affect this. That's why I ultimately want to be doing a beam search or something else. Well, a beam search is a good heuristic. Okay. So, and as you've seen in class and then the homework, this is very reminiscent. Like, this is the same generative model as we have with n-grams, right? What they're saying, you've heard of this many times probably by now. Each time stamp, we extended each partial, as soon as the EOS symbol is appended to a hypothesis, it is removed from the beam and is added to a set of complete hypotheses. While this decoder is approximate, it is simple to implement. Interestingly, our system performs well even with a beam size of 1, and a beam size 2 produces most of the benefits of beam search. This is interesting that they only need a beam size of 2. Oh, the thing I was talking about that you have probably seen by now was somewhere in the paper, they were like, EOS have no non-zero probability, and we know that at some point of time, we're going to hit an EOS token, and that's why we're producing a valid probability distribution over outputs of all possible lengths. And that's something that our professor talked about in one of the early lectures, that by using this EOS token, we're building a valid probability distribution, even though the outputs can have different lengths, right? And we have a valid probability distribution over different length outputs. And that's great. Okay, we talk a bunch about reverse and source sentences. And again, by reversing the words in the source sentence, the average distance when the corresponding words in the source in the target language is unchanged. However, the first few words in the source language are now very close to the first few words in the target language. So the problem's minimal time lag is highly reduced. And well, gradient descent appears to train better in those conditions. Okay.
That was strictly for translation though, right? Because that's
Yeah.
an inherently important aspect. Okay.
Right. So yeah, so this is, and again, they're using this for translation. This was, I think, the first instance of actually building something that takes and sequences an input and produces a sequence of a different length. But this is the same architecture you could use for generating replies to Gmail emails, right? Same stuff. Reply in your case is going to be a translation. Like it's the exact same architecture. Again, if you use this this layout over here, this guy, you can build a classifier if you want. So many different applications. Very cool. Cool. What's next? Here they talk about, so a PCA projection. Probably many people know this better than me, but the way I understand it is that, let's say you have a bunch of 300-dimensional vectors. You can't represent them because humans are not very good with dealing with 300 dimensions. You're interested in the two most important dimensions, so you take the two most important dimensions as measured by variance, right? Where the variance is the largest, and it seems like your vectors pay the most attention to that, and then you project that, right? So here, if out of your hidden states, you pick two most important dimensions, you can see this interesting shape where you have ultimately very similar sentences. John admires Mary, John is in love with Mary, Mary admires John, and they're clustered together here and here. And what's interesting is this, notice how Mary is in love with John, this sentence shape, right? The outline here in this cluster is the same as in this cluster, right? John is in love with Mary is also in the middle, just like here. And Mary respects John is also in the bottom of the cluster, just like John respects Mary over here. And Mary admires John is at the top as John admires Mary. So there's no particular meaning to these representations, but they're just interesting to see how they cluster. So again, these are hidden states. These are projections of our hidden states. Ultimately, we see that similar sentences are being encoded similarly in our hidden states, and that's great. That's what we wanted. Then they give a bunch of examples. They, of course, were translated into French. Okay, something I wanted to mention is that, you know, a lot of ML papers, they're obscure in a way that they don't describe their architecture very well. They feel very almost hostile to other researchers, and they're always like, we're the best, or our results are the best, everyone else sucks. But this paper felt very respectful and very pleasant to read. First, because it explains things in details in pretty simple words, and it pays a lot of respect and gives homage to other researchers. So, for example, over here, likewise, someone attempted to address the memory problem of someone by translating pieces of the source sentence in a way that produces smooth translations, which is similar to a phrase-based approach, whatever. And apparently that approach didn't work very well. So the authors of this paper say, we suspect that they could achieve similar improvements by simply training their networks on reverse source sentences. So they're like, you did a good job, and we found this very weird improvement that we can't even explain very well, that we get a lot of improvements, but just reversing the input sequence. We suggest you do the same, you will probably get a bunch of unexplained results. So that feels very, good citizenship. So very much like that about this paper. Okay, so boom, boom, boom. The conclusion, it's a long conclusion, but basically they trained a machine translation model, right? That worked very well on different long sentences. And this is the most surprising thing. Again, RNNs have a little bit of a problem with processing long sentences and long dependencies because they tend to forget stuff over time. This thing worked for them, especially with reversed inputs. And yeah, so this was the first time a simple, straightforward, and a relatively unoptimized approach outperformed a statistical machine translation system. And yeah, so this is the thing. Any questions, thoughts, feedback on how you would improve this, change this, or maybe something doesn't make sense to you at all?
I just have a comment on your like citizenship thing. I think that's super cool. And I noticed there's Jeffrey Hinton on the acknowledgements and Google Brain team.
Right.
So I just wonder if there's like some cultural influence on some of that.
Yeah. These are definitely superstars in the field. Yeah.
I know you touched on figure 2 in 3.8 and part 3.8, the model analysis.
Right.
Did you go over what the X and Y axes refer to? Because that is, to be honest, throwing me.
That's my favorite. Do you by any chance have a background in physics or something? No?
No, not at all. Is that why you're understanding this?
No. I just know someone who is not a physicist at all, but like because they have a background in physics, they always yell at people who don't assign their axes, because that's like an important thing in physics. You never look. You always yell at people that don't label their axes. It's very important to physicists. Maybe you have.
You can't tell me this is completely arbitrary. Like the numbers have to align to something, right?
Right. Yeah, exactly. I mean, no, I have the same knee-jerk reaction. So a PCA, what is a PCA projection, right? So what they're trying to represent here is a hidden state. And again, a hidden state is a vector and of dimension, let's just say 300. Now the problem is that I could try really hard, but I would not be able to print a 300 dimensional vector representation on a piece of paper. And if I did, people would not understand me and they would think I'm weird. So what people are good though, understanding 2 dimensions. So the idea of PCA is to pick the 2 most important dimensions out of this entire vector.
Oh, okay, that makes a lot more sense.
And the 2 most important, okay, and I read it, I spent 30 seconds trying to understand what is PCA, and I'm not, don't tell professor I said this, but I probably am explaining things incorrectly, but the most important dimensions are measured by their variance, right? If most of the values are centered around 0 and 1, should I probably typing today, sorry. And then the last 2 values are from -100 to plus 2000, right? Then I probably should pay a lot of attention to the last 2 values, because it seems like they represent a lot of information and a lot of variance in my vectors. So what they're saying here is that they're picking those 2-dimensional projections. They're picking just two values from the long vectors. They're actually using 1,000 value vectors, hidden state vectors, and they're projecting this. So answering your specific question, the particular values do not carry any meaning here whatsoever. This is a neural network output. But how did they pick these 2 axes? They just picked what they deemed the most important ones out of the 1,000 that they had. Okay,
that makes a lot more sense, especially with you focusing on that, the comparable curves in the first graph to the left. That
yeah, that's really
contextualizes it a lot.
Yeah. Thanks for the question, though. It's a good one.
Yeah, thanks for the explanation. So I'm new to looking at machine translation. Are these findings basically only applicable to French?
No. So what makes you think it's applicable to French?
Truthfully, no idea. I mean, I see some of this reversing and I wonder how that would go with right to left languages, going from left to right to left. Looking at languages that are not Western, I mean, French and English.
Yeah,
Quantify the differences in languages, I'd imagine they'd be pretty quantitatively similar.
right.
Both
That's,
like Hebrew.
I think, so there is two parts to this paper. The first is the architecture, and the second is, hey, we reversed inputs and it worked much better. So the thing about the reversed inputs, my guess would be it depends on the exact task you're doing. The thing
Sure.
about the architecture, it doesn't. So the architecture is still general and applicable. And again, you could generate responses to email. You could generate responses to English emails in French if you want. It doesn't really matter.
Okay.
But it's the same architecture one way or another. But the thing about the reverse input, right, they don't give a very good mathematical explanation for it. And as you said, whatever explanation they give, it doesn't really apply to all languages. So it probably won't work everywhere. And I think maybe you should email them.
No, but the reversing is fascinating. What is the idea that they were just throwing things at the wall to see what stuck? I
would think a lot of ML research is like, okay, let's tweak this thing over here a little bit.
Sure.
Paper about it. This one specifically is much more fundamental than that, but I'm just saying that it happens a lot in the field.
Sure.
Okay. Any other thoughts? Cool. If not, then we can end 4 minutes early. All right. Thanks everyone for coming.
Thank you.
Station.
Bye.
Thank you.
Bye.